Okay. All right. So I'm going to finish the worksheet that we started last class. Okay. So I have actually posted the posted the recorded lecture. So if you go back to the recorded lecture, you will have the solution to worksheet. This is worksheet 9 that we are doing. Okay. All right. So from last class worksheet, we found C2 to be 0, and then we plugged in this when x is equal to 3. So 3 is where you have the transition point. So for the two segments, the equation for both segments. So we did find the equations for both segments. What happened to this? Okay. Okay. Okay, now it's clearer. So for segment AB, so this is your gradient for the elastic curve. So if this is your beam, the elastic curve is when it actually deflects, okay? And this is the deflection. So you have, this is for segment AB, okay? Only for segment AB. Then we found similar, another two equations for segment BC. So if you look carefully, this was the problem we were solving. And this B is our transition point, okay? So, sorry, when at C is not our transition point, B is our transition point. So you will see at C is where your x is equal to 3. So this distance is x is equal to 3. And obviously V is 0 when x equals to 3. So if you plug in, put x equals to 3 meter and v equal to 0 in equation 4. Equation 4 would be this one because C falls in the segment BC, okay? Falls in this segment C. So we have to use equation 4. So if we plug that in, this is what we get. Now remember, B is our transition point. So dv dx at x equals to 2 using the segment AB equation must be equal to dv dx when x is equal to 2 using the segment BC formula. Okay, so if we do that, this is where we left off last class. So if I want to plug those in, this is what you will see actually. So at B, so I'm going to say, so this is my first equation, dv dx is equal to 50 x squared plus c1. So I'm going to say 50 x squared would be 2 square plus c1, okay, must be equal to, this is my equation for the segment BC for the slope. If I plug in x equals to 2, that must be equal to this, okay? Because this EI dv dx at x equal to 2 should be same as EI dv dx at x equal to 2 for the segment BC. So I'm just going to plug those numbers in. So I have 50, 2 square, x is equal to 2 in this case, minus 150, 2 minus 2 square plus C3. And you will see that we'll get C1 is equal to C3. Okay, so again at B, we're going to say that x is equal to 2 meters. And we're going to say, hey, the deflection at x equals to 2 meter, minus means using the segment AB. and the deflection at x equals to 2 meter. For the segment BC, they must be same. So this is for segment AB formula, this is segment BC. So if I do that, so again, I'm going to use equation 2. So if I plug in here, x equals to 2, whatever EIV I will get, it must be equal to, if I plug in x equal to 2 in equation 4. Okay. So if I do that, so if I'm doing that, so this is what I will get. So 50, let's look at this equation 2, 50 by 3x cube. So I will plug in 50 by 3, x cube is 2 cube, and plus, okay, C1x. So I'm going to say 2 times C1, and C2 is 0. If you remember, that's what we got last time, so I'm not going to write it. So now this must be equal to whatever I will get from here. Okay, so that is going to be equal to 50 by 3, 2 cube, minus 50, 2 minus 2 cube, plus 2C3 plus C4. Okay, so I end up getting 2C1 is equal to 2C3 plus C4. Now if I putting C1 equal to C3 above, in this equation, if I put, in the above equation, if I put C1 equal to C3, then I end up getting, so let's put 2C3 is equal to 2C3 plus C4. Now remember, C4 is 0. Wait, there is something missing here. So we got C4 to be, oh, sorry, 3C3 plus C4 is equal to minus 400. So C4 is not 0. So from equation, this is my equation 5. Okay. So this is what we get. So what do we have? This is from here we can say C4 is equal to 0 because these cancels out. So C4 is 0. So we can putting C4 equal to 0 in equation 5, which we obtained last time over here. So 3C3 plus C4, this is what I'm writing right now, is equal to minus 400. So from the above equation, we got C4 to be 0. So my C3 is minus 400 by 3. And remember, C1 is equal to C3. So C1 is also equal to minus 400 by 3. So now I'm going to write down my equation for the slope as well as equation for the deformation. So this is,
Professor?
Yeah, go ahead.
When you reference equation 5, can I see the equation 5 really quick?
Yes, sure.
Oh, that one.
Yeah.
Professor?
That we, just a second, Runa.
Yeah.
That we obtained by putting x equals to 2 meters and v equal to 0 at location C.
Okay.
Yes.
Okay. Thank you.
Yeah. So Professor, I got in late in the class because I couldn't find the link. So I missed a few lines. Can you please tell me where you started from today?
I started from here, the blue writings.
Okay, yeah, I got it. Okay, cool. Thanks.
All right. So now I'm going to say, okay, equation for the slope. So equations. Let me just check one more second that I am recording my lecture. It's getting recorded. Okay. Okay. Equations for slopes. So that's going to be for segment AB. So that is my equation 1, but right now I know all my constants, so I know how much is C1, so this is equal to, I can write EI dV dx is equal to 50 x squared plus C1. Now C1 is minus 400 over 3. And I can also write down this equation is only valid when x is greater than or equal to 0 meters, but less than or equal to 2 meters. Okay, so that's my segment AB. Now I'm going to look at segment BC. That equation would be equation 3 here, this one. And that's EI dV dx is equal to 50 x squared. The only difference is now I know how much is my C3. So let's write it down. Now instead of C3, I'm writing the value of C3, which is negative 400 over 3. And this is valid for x greater than 2 meter, but less than or equal to 3 meters, okay? Greater than or equal to 2 meter. Now let's look at the equations for deflections. Segment AB. So that is equal to, so that will be my equation 2. So 50 by 3x cubed plus C1x, C2 is 0. C1 we just have to plug in minus 400 over 3. So let's write it down. So that is your that is the equation. Oh, no, that is for the other one. Sorry. The equation is actually 50 over 3 x cubed minus plus C1x. C1 is minus 400 over 3 times x. So this is valid for x greater than or equal to 0 meter, less than or equal to 2 meters. And for segment BC, it is going to be the last equation, that is equation 4.
Professor, didn't we need to find C2 as well?
C2 we found it last class. We found it to be 0.
Oh, got it. Thanks.
We used the location
Oh yeah, I see it.
A.
Thank you.
Okay, so so the last equation is equation 4, 50 by 3x cubed minus 50x minus 2 whole cube plus C3x. Now C4 we found it to be 0, so I'm not gonna write it. We just have to plug in the value of C3 and that's it. So that's going to be 50 by 3 x cubed minus 50 x minus 2 cube minus 400 over 3 x. Now this is again valid for x greater than or equal to 2 meter, less than or equal to 3 meters. So we are actually done. That's what the problem asked for part A. If I go up, for part A, it asks for the equation for the slope and deflection, okay, for the segment AB and BC. We found it. Now in the second part, it's asking me what is going to be the maximum deflection of the beam. Okay, now I do not know where the maximum displacement will be. Okay, but if you consider this beam, to be bending. So if I consider if this is my beam, so I'm in part B now. This is my beam. And if it is bending, so it will bend something like this. Now, I don't know where this maximum deflection is going to be. I don't know. So I need to find out. But remember, say wherever the maximum deflection is, the slope at the maximum deflection is always 0. Okay. So, so slope of the elastic curve at maximum deflection is 0. But I don't know whether my maximum right now, the way I have drawn it, it's seems like it's in AB, but I actually don't know. The maximum deflection can be in the segment AB, or it can be in the segment BC. I don't know. So I'm going to put the slope that I have here first equal to 0. I'm going to put this slope dV dx to be 0 for segment AB and solve for x. That will give me where the slope of the elastic curve is 0, the x location. I'm going to do the same thing for my I'm going to do the same thing for my segment BC and put this to be 0 and again solve for x. Okay, so you will see one of the segment will give you some imaginary number, invalid number. So that means that obviously you do not have a maximum at that segment. Whichever will give you a valid number, whichever segment will give you a valid x value, that's the segment where you're going to see the maximum deflection. So let's plug this in. So I'm going to put this EI dV dx. So for segment AB, so I'm going to say we have this, the equation of the slope is this 50 x squared minus 400 over 3. So if you go back, this is
Professor, Dakota wants to know why the slope is 0.
Slope is 0 because if you see wherever the maximum will look something like this, right? So at the maximum, you're going to see a slope to be 0, right?
Got it.
Think about it. Okay, so if I draw something like this, you have a slope somewhere here. And here, if I draw a tangent, is somewhere here. But if you have a maximum or a minimum, if you draw a tangent, it will be horizontal, telling the slope to be 0. Similarly, if I have a maximum, if it deflects like this, at something at this location, your slope will always be 0. Does that answer your question? Is that okay?
Yeah.
Should I? Okay.
No, you're fine. I think Dakota, that was Dakota's question.
Okay. So if you plug
I
in
think his microphone's not working.
dV dx is 0. Yes, people. Everybody good? Okay. So dV dx is 0. So if I plug in, so this equation.
Math. All right, next time you ask, I'll get it.
Okay, whoever is talking, you can actually mute yourself. Please mute yourself.
Short film.
Okay. So 50 x squared minus 400 by 3 is equal to 0. Okay. So this is what we get. So if you solve for, everybody please mute yourself. Okay. So this is what we get. So now you solve for x. If you solve for x, we see x is equal to 400 divided by 350 root over, okay? My answer would be plus minus 1.6331 meters. Now, obviously, length cannot be negative, so you have to take the positive number. So it's 1.6331 meter. Okay, this is what we have. Now for segment, so I'm gonna do this for segment BC. So for segment BC, this is my equation. I'm gonna put it to be equal to 0. So I'm gonna write down this equation. I'm going to actually expand this. If you expand x minus 2 whole square, you're going to end up getting x squared minus 2x plus 4. Okay. Then minus 400 over 3, because the last number is this. Okay. Now we know that dv dx is 0, so we can put this to be equal to 0. Now if you solve for it, this is the equation you will get. Now, if you solve it, you will see that you're going to get some imaginary number, invalid number. So we can conclude that the maximum deflection occurs at x equals to 1.6331 meter from A within segment AB. Okay, so if I draw my right, so if I draw it, you're gonna see your maximum. So this is C prime. This is where your Vmax is. Vmax. And the distance from here to here is 1.6331 meters. Okay. So I can maximum deflection. Which equation should I be using? Equation, I will be using the equation for segment AB. That means this is the equation. And instead of x, I'm going to write down 1.6331. So let's write down the equation first. So the equation is 50 over 3x cubed minus 400 over 3 x. So my Vmax is going to be EI Vmax. That's equal to 50 over 3. X is going to be 1.6631 cube minus 400 over 3, 1.6631. Okay. And we know E and I. So my Vmax is, all I have to do is divide the EI with whatever number you get. 0.6631 cube minus 400 over 3, 1 over. If you recall, your modulus of elasticity is 12 times 12 gigapascal. That means 12 times 10 to the power 9. And I is given.
Professor, that's 6331 or is it 6631?
Let me see.
Because in the diagram you wrote 633. Is it the same thing? Or
6631 actually. Let me see, where did I?
over here, so with the one with which you wrote with the purple
Oh yeah,
marker,
okay, 6631.
it's 6631. Okay.
Yeah, if we solve, okay, I think, let me see.
Or there it's
Let me check it. Let me check. I could be okay. 6331 actually.
Hmm.
Okay, I'm making a mistake here. Okay, and modulus of elasticity. Okay. And use modulus 12 gigapascal. Okay, the problem doesn't actually, I missed out the oh yeah, we have, it's given. I did not miss out. It's given 40 and 80. Your cross section is given. So let's calculate I. So I don't know yet. So I is equal to BH cube over 12. So B would be 20 and H would be, B is, sorry, 40, H would be 80, okay? So it's in millimeters. So I'm going to change it to meters. And we just have to now calculate that. So it's 1.7067. So let me just write it down here, okay? (1.7067) times 10 to the power negative 6. So if you do that, so this is 1.7067 times 10 to the power negative 6 meter to the power 4. Okay, let me recheck this 1.66339 or not. 400 divided by 3 divided by 50. Yeah. All right. So this is what, so if you actually do this, if you do this entire calculation, the one that I have written, your Vmax will be negative 7.08 times 10 to the power negative 3 meters. Why is it negative? Because the deflection is downwards. So remember, in the superposition method, you have to manually put the signs in, whether it's a positive slope, negative slope. But here it's automatically, it will give you, if it's a downward deflection, you'll get a negative deflection. If it's a upward deflection, you get a positive deflection. So so I can write it down as 7.08 millimeter downward. Because I gave this downward sign, I can remove this negative sign. So that is my Vmax. Okay, any question? Okay, that's my Vmax.
Quick question.
Yeah, go ahead.
Could you just pause for a sec? Like if you could scroll up just a little bit. Trying to keep up. It's just that when you write something down, you scroll way back up and doesn't give us enough time to copy down all the equations.
Okay.
Just for a quick second.
Sure, no problem. But I will post this recorded lecture as well.
I understand.
Professor, we found Vmax by plugging in the I value, right?
I plugged in the I value here.
Oh, okay.
Right. So remember EI. So you know you have to put this bring this EI down, right? Get your Vmax. So that's
Oh.
what I did.
Okay. Thank you.
Let me know if you all are done writing, okay? Or if I need to scroll up or down. Is everyone done writing?
I'm still copying. Just one
Okay.
minute.
Yeah, no problem.
I'm finished.
What about others? Everybody good?
I'm good.
Good.
Done.
Okay, all right. So this is the end of beam deflection. Okay, we have looked at two methods, the double integration method. We just looked at one problem using the double integration method, and we did go through another problem using the superposition method. Now in the exam, if I give you superposition method, I'm going to give you the tables that you need. Okay, you need to be able to read the tables. Now with this, we are finishing the beam deflection. If you recall last class, we started talking about state of stress. Okay, we talked about you can take a small stress element from a body and express the stresses acting on it. So we looked at sign convention here. Remember the X face. So X face would be the faces. X faces are perpendicular to x-axis and y faces are perpendicular to y-axis. Now the positive X face is actually, you will see it, this will be your positive X face. This is negative X face, okay, because it is facing the negative x-axis. This is your positive Y face, negative Y face, okay. And we talked about, hey, if we are rotating the same element, if I want to look at it from, say, for example, rotate it, what are going to be the stresses on this rotated element, okay? So you can actually get those stresses from stress transformation equation. We talked about the stress transformation equation last class, where theta is the angle of rotation. So we talked about, here's what we talked about, that if this theta is going counterclockwise from x to x prime, then it's a positive theta. And if you know that angle theta, and if you know the stresses in the x, y direction, so this is always the plane stress condition that we are looking at. What does plane stress condition mean? stress in the z direction is 0. That means sigma z is 0. You do not have any stress in the z direction. Only under that circumstances, these are the equations. And if you plug in theta to be the angle of rotation, plug in the sigma x, sigma y, or tau xy, you will get the stresses in the new rotated direction. Okay. Now we talked about stress invariance, like we talked about, hey, this is the stress element that you have. Now if I rotate it, you see different stress. If I rotate it even more, you will see different stress. Okay. But in no matter how much you rotate or anything, this is, you will see summation of the normal stresses is always same, no matter which direction you're talking about. Like for the blue, for this blue stress element, so this is your sigma x, say this is your sigma y, and say these are your stresses, tau xy, and shear stress. And for the purple one, say this is your sigma x prime, this is your sigma y prime, and this is your shear stress, tau x prime y prime. See the shear stress like this. So for the blue stress element, what is the summation of your normal stress? Is sigma x plus sigma y. Whereas for the purple one, your normal stresses are sigma x prime and sigma y prime. So what is the summation? Sigma x prime and sigma y prime. So you will see that if you sum this, whatever value you will get, you will end up with the same value if you sum sigma x and sigma y. So that's why it is called stress invariant. So there are more than one stress invariant. We're just looking at one here. So this is one of the stress invariant that you're gonna see. Now, we left off here last class. We're gonna start with what is called principal stresses and directions. So remember, for any structural analysis, our goal is to know, hey, what will be the maximum normal stress this structure is going to see? What will be the maximum shear stress this structure is going to see? Once you know the maximum values, you compare it with your yield strength in tension, or you compare it with your shear strength, and see whether your values are within the limit or not. So that's how we ensure that nothing fails. Now, now what are principal stresses? So if you remember, what did I say? If you look at a stress element without rotating from any structure, if you take a small 2D section and look at it without looking at it from any other angle, and then if you look at it at a different angle, your stresses are not going to be same. Your stresses are changing. But so this is your, say, without changing any angle. So you're just looking at one small element from your structure. Now, say you rotated it by an angle theta 1, and this is what you see, and the stresses are different. Okay, not theta 1. Say you rotate it by an angle theta. So I rotate this by an angle. Okay, so I rotate this by an angle theta, say. Okay, so now the stresses I'm going to see in the theta direction, theta prime, x prime direction, these are my stresses, sigma x prime, sigma y prime. So they're different, okay? They're not same as sigma x. So if you keep on rotating it, depending on what your value of theta is, your stresses are going to change until you will come to an angle where you will see that your shear stress tau x prime y prime becomes 0, and you only see normal stresses. Those stresses are called principal stresses. Okay, and the angle where you will see these stresses is are principal directions. Now, why are they called principal stresses? Those normal stresses you will see will be the maximum stress at a particular location that you're going to be seeing. Remember, we are looking at stress at this particular location at different direction. Okay, so if you have a stress element like this, so you're basically looking at a stress at this point, okay, at this point O. All right, so when I rotate it, say when I rotate it, it looks something like this. This is sigma x prime, sigma y prime, and now you have your shear stresses. Okay, but you're still looking at the stress at the location O, but say at an angle, say theta. So you're looking at the stress at a point from different angles. Okay, these stress elements, the squares that I draw, are very small. Okay, so we are always looking at this, the stress at this point, but at different angles. So if so with the angle, your stress is changing. So at two specific angles, you will see that your shear stress is 0. You only see normal stresses, and those are the maximum and minimum normal stresses at that location, at that point. That maximum and minimum normal stress at that location or point are called principal stresses. And the two angles at which they occur are principal directions. So let's look at this. So so the directions are designated as theta 1, theta 2, and the maximum principal stress is designated as sigma 1, and the minimum principal stress is designated as sigma 2. The angle associated with sigma 1 is theta 1. The angle associated with sigma 2 is theta 2. Okay, so if you see the angle between x and x prime, where x prime in the x prime direction you are looking at sigma 1, that angle is theta 1. And the angle between x, now if you want to look at the sigma 2 and consider x prime to be acting in the sigma 2 direction, like you keep on rotate it by another 90 degree, then your x prime will take the position of y prime will take the position of x prime. So this is what you will see. And you will see that the angle between x and sigma 2 is theta 2. So that's associated with sigma 2. Okay, so what do we see? Theta 1 and theta 2 differ by 90 degree. And sigma 1, sigma 2 occurs in two planes, okay, which are 90 degree to each other. Okay, so any question at this point? Please unmute yourself and ask question. If you're okay, then you can actually put it in the chat. I can see some.
Is this coming in the quiz on Thursday?
No, this is not beam deflection. This is stress transformation, but this is very important for your final exam. Okay. Any question, people?
You might have already clarified it, but I just want to ask again. Isn't it technically the case where sigma 1, if it's maximum, then sigma 2 would be minimum? Wouldn't that be 0?
No, it's not always 0. You can have a negative value.
Oh, okay. Yeah,
Or you can have two positive value. Sigma 1 will be the higher of the two values.
Okay.
Professor, what did you say about the sigma 1 and sigma 2? How do they differ?
The planes that at which they act, if you look at it, so if sigma 1 is acting in this plane,
Yeah.
right?
Hmm.
And sigma 2, so sigma 2 is acting in this plane, right? The two
Yeah,
planes
so-
are what, at 90 degrees to each other.
Right.
Okay, so the angle at which you're going to see sigma 1 working is theta 1 from x direction, okay?
Yeah.
And the angle at which you're going to see sigma 2 working from x is theta 2. Okay,
They differ by 90 degrees.
correct.
Okay. Please. I got it. Okay.
All right, now how do we calculate them? Okay, so principal directions can be calculated using this equation. Okay, so if you know shear stress in the xy plane and normal stresses in the x and y direction, you will end up you can calculate theta 1 and theta 2. The two solutions are 90 degrees to each other. Okay, and principal stresses can be obtained. So you can also, if you can calculate theta 1 and theta 2, if you know your theta 1 and theta 2, that means these are the directions in which your principal stresses are acting. If you plug your theta 1 and theta 2 in here in sigma x prime and sigma y prime, if you plug in theta 1, you're going to end up getting sigma x prime to be sigma 1 and sigma y prime will give you sigma 2. Or if you plug in theta 2, here sigma x prime will give you sigma 2, sigma y prime will give you sigma 1. So what I'm trying to get at is, if you know one of the angle and plug these in the stress transformation equation, these three equations are called stress transformation equation, you're going to get the principal stresses. And if you plug in theta 1, theta 2, you will see that tau xy will turn out to be 0. Okay, but there's another shortcut formula that you can use. But you will see that I will have to use this. Even I will solve worksheet problems with you all. You'll see we are going to use this equation for checking the angles. Okay, so we have sigma 1 and sigma 2. So you can also use a shortcut formula, which is this formula. Okay, you can directly plug in sigma x, sigma y, and R is equal to sigma x minus sigma y by 2 whole square plus tau x xy square. So if you plug in the values directly in this equation, you're going to get your R here. And if you plug in the values, you're going to end up getting sigma 1 and sigma 2 directly. Okay. Now, sigma 1 and sigma 2 act in principal planes. These planes are called principal planes. These planes are called principal planes, okay, where they act, all right? So they act in principal planes. They are defined by the angles theta 1 and theta 2, okay? And if principal directions are plugged into stress transformation equation, you will see that tau x prime y prime, as I have mentioned, it's going to be 0. All right. So basically, you have to usually what we do is in a problem, they're going to give you sigma x. They're going to give you something like this, a stress element like this. They will give you the values that are acting, working on this stress element. From there, you should know how much is your sigma x, sigma y, tau xy. Now, if you plug these values in this equation, you're going to get sigma 1 and 2. Okay. And if you plug these in here, you're going to get theta 1 and 2. But you do not know, basically, you're going to get 2 theta values. You're going to get 2 theta values. But you do not know which one of those theta is going to be theta 1, which one of them is going to be theta 2. So that's why what you have to do is plug in one of the theta value in, say, sigma x prime equation over here. Okay. one of the theta in here and find out how much is your sigma x prime. So, and then compare it with whether it's sigma 1, whether it's same as sigma 1 or whether it's same as sigma 2. If it is same as sigma 1, then that theta is your theta 1. If it is sigma 2, then that theta will be theta 2 and the other angle will be theta 1. So this is to verify which angle goes with which principal stress. Okay, you have to verify that. This you will get much clearer when I'm going to solve a worksheet problem next class. Next class, maybe not this Thursday, we'll go over your midterm next Tuesday. All right, maximum in-plane shear stress. Now we looked at these sigma 1 and sigma 2. These are what? Sigma 1 and sigma 2 are normal stresses. Okay, so they only happen at 2 different directions at a particular location. Okay, and what is the useful? Why is it useful? Why do we even bother to know that? Actually, sigma 1 and sigma 2 tells us the maximum and minimum stress that location is going to experience, and that allows us to make a decision whether it's going to fail under normal stress or not. Okay, at that location. Now, maximum, similarly, if you keep on rotating, so this is my if this is my stress element, and if I keep on rotating it, I will come across another angle at which I'm going to see maximum in-plane shear stress. Why is it in plane? Because this is a plane stress problem. So mostly there is no stress in the Z direction. That's why we call it in-plane shear stress. Okay, so at a particular direction, the shear stress, it will be maximum. And that direction for maximum shear stress, you will see, is 45 degrees to the principal direction. So if you, one of your principal direction is theta 1, you will see that the angle at which you're going to see maximum shear stress is 45 degrees to that to theta 1. Okay, so you will see that it is 45 degrees to the principal direction. So unlike the principal stress case where your shear stress is 0, your normal stress is not 0 when you see maximum shear stress. Okay, so there will be normal stress acting on planes for maximum shear stress. Okay, so wherever you see maximum shear stress, not only your shear stress is maximum, you're also going to see some normal stress there. And the value of that normal stress is going to be average of sigma x and sigma y, which is sigma x plus sigma y divided by 2. Okay, now how do I know at which location I'm going to see maximum in-plane shear stress? This is the equation that you're going to be using. Again, you will end up with 2 solutions. Okay, the 2 solutions will again differ by 90 degrees. All right, and the maximum shear stress value you will obtain by using this equation, plus minus r. R you can get from here. Okay, so you have a plus r and minus r. So we have a maximum and a minimum shear stress value. So that's why you have 2 theta, one for the maximum, the other for the minimum. Okay, and remember theta is 45 degrees to your principal direction always. Okay, so if I were to draw, so if this is the stress, this is how the stress element will look like if you are only looking at principal planes, and this is how the stress element will look like when you are looking at maximum in-plane shear stress. Okay, see, you have tau max, shear stress is maximum. The angle between x and x prime is designated as theta s. That's, you're going to use this equation to get your theta s. And obviously, you do have normal stresses acting there. And the normal stresses are sigma bar. Sigma bar is nothing but average of the two normal stresses. Okay, so this is how the stress element will look like for maximum in-plane shear stress. So you will be given a problem like this, and then you'll be asked, hey, what is theta s, what is tau max, and then draw the stress element. So this is the location we're interested in. So draw the stress element showing all your tau max and your sigma bar, everything. Okay, any questions so far, people? Am I missing a slide? Okay, no, I'm not. Okay. All right, any question, people, for principal stresses and maximum shear stress, in-plane shear stress?
I have a question. Whenever we get two thetas, if the difference is not 90 degrees, that means we got it wrong?
Yeah, if for maximum in-plane shear stress, the two theta should differ by 90 degrees. As well as for principal planes, the two thetas must differ by 90 degrees.
And can we find one of them and subtract or add?
You can add, yeah, you could.
So we add it or subtract it?
It's going to depend on the problem.
Okay, thank you.
Anybody else? So this is going to get more clearer when we'll be doing worksheet number 11, I believe. Everybody's good? All right. So having said that, this concludes our stress transformation equations. Okay, these are stress transformation. These are solving using equations. Okay, there's another method of visualizing these stresses. Okay, so long time back, there's this German scientist, Otto Mohr, who actually visualize this stress transformation in terms of a circle. And under his name, that circle, people call that circle Mohr's circle. Okay, so the one that we talked about a few minutes back, those are all the equations that we used, but you can also find out what are the stresses going to be like for each of the planes, for different planes, if you know your Mohr circle. Okay, so Otto Mohr visualized the change of stress components with rotation, rotation of the coordinate axis in terms of a circle. That circle is called Mohr's circle. And the equation of that circle is this. This is the equation of that circle, where R, remember the R that we looked at in the previous, in the previous equation, the R. Okay, this R. This R is actually the radius of that Mohr circle. So this is the R, this is the radius of the Mohr circle. Now this sigma bar, okay, this sigma bar is the center of the Mohr circle. And this is the radius of the Mohr circle. Okay, and so that this is the center, you can see. Now Mohr circle, the y-axis of the Mohr circle is designates the shear stress, and the x-axis designates the normal stress sigma. Okay, so this is how a Mohr circle will look like. I mean, it can look very different as well. You can have a Mohr circle like this. You can have a Mohr circle. You can have a Mohr circle that looks like this. So the different more depending on the problem, your Mohr circle will change. But this is how a generalized Mohr circle will look like. you can see this is my sigma bar is the center, x coordinate of the center of your Morse circle, and the y coordinate is always 0 for plane stress condition. Remember, for plane stress condition, that means sigma z is 0. Okay, and so there are some key important details that we have to remember for Morse circle. We will learn how to draw a Morse circle, or how to identify X face, Y face from a Morse circle for different angles. Okay, so let's look at this. Stress on the Y face on a Morse circle, stress on the Y face is drawn as sigma y tau xy. Say for example, I'm gonna say, hey, this is my Y face. And how do I know, how do I actually designate this point? I will know my sigma y. So this is going to be my sigma y, and this is going to be my tau xy. Okay. Now stress on the X face is drawn as sigma x minus tau xy. That means obviously your X face will be X and Y faces are 90 degrees to each other. On the Morse circle, they'll be twice the angle. So 2 times 90 degrees, 180 degree. So if you go 180 degree, you end up with this point. So this will be my X face. Okay, and this is my sigma x. This is my minus tau xy. So what does this mean? This means that your whatever shear stress you see on your X face, in reality on that particular stress element, the shear stress will be of opposite sign. So if I see, say this is minus, say 90, and say this is plus 90, then if this is my X face, I will say, hey, minus X face will always have the signs of the shear stress flipped, the actual sign. So if this is my problem, say I have sigma x, sigma y, and say tau xy, and my tau xy is a positive number, 90. Okay, you will see on the X face, I have to put it as minus 90. I have to flip the sign. Okay, so the best way of knowing, if I give you a Morse circle and tell you, hey, this is a Morse circle, this is Y face, this is X face. Tell me what is sigma x, sigma y, and tau xy. So it's easy. Definitely from X face, you can get your sigma x. Definitely from your Y face, you can get your sigma y. So you can easily get them. Now, when it comes to tau xy, you always read it from your Y face. Then in that way, you don't have to switch your sign. Whatever value you get, that's the real shear stress acting on this particular stress element. So if I read it from Y face, I'll get 90, say megapascal, for example. But if I read it from the X face, I have to flip the sign. I will read it as minus 90, and I know that, hey, the shear stress on the X face is always of opposite sign to the real case. So if it is reading minus 90, then for the real case is plus 90. Okay, so I always advise students to read your shear stress from the Y face, not from the X face. Okay, these are certain things that you will need to remember. So stress on X, so remember, stress on X face is 180 degree from the Y face. That means the actual angle is 90 degree. On the Morse circle, the X and Y face, or X prime and Y prime faces, are twice the actual angle. Okay, so the sign of shear stress on the X face of Morse circle is reversed compared to the actual sign of the X face. Okay, actually the shear stress is on the X face is positive, but on the Morse circle, the sign will be reversed, flipped. Okay, properties of Morse circle. The angle between two diameters on the Morse circle. So say, for example, I have two cases here. And I have another case. I'm just drawing it separately. I don't want to overlay the drawing. So I have sigma x prime y prime. Now I rotated it, okay? So I have tau x prime y prime. So I have, so if I draw my x and y face, say I get something like this. This is my y face, this is my x face. So I get a diameter, something like this. And say the angle of rotation is, say, theta. Okay, so when I actually draw my x prime and y prime, say I'm going to get something like this, for example. So this is going to be my x prime, this is going to be my y prime. So what is the angle between the two diameters? This is the angle. So the angle of transformation was theta. Remember, I rotated this by theta. But on the Morse circle, the angle of rotation is going to be twice of the actual rotation. So you're going to see 2 theta. Okay. So this is something we have to remember. The angle that we see, the angle of transformation is twice the actual angle of transformation, the transformation. Okay, so on Morse circle, the angle of transformation appears twice the actual actual angle of transformation. Now the stress at x prime face at angle theta from the x face can be obtained by going, okay, so if this is my x prime face, okay, so you can find out what is going to be what is going to be sigma x prime, okay, by traversing from the x face, okay, if from the x face, if you go twice the angle theta, you will reach your x prime face, and you can directly read your x prime, sigma x prime, from the Morse circle. So that's what it is saying. Stress at any x prime face at an angle theta from the x face can be obtained by going 2 theta around the circle. So you'll have to go 2 theta from x. If you go 2 theta from x face, you will reach x prime face. And you can directly read your sigma x prime from the Morse circle. In order to do that, you will need protractor, okay? And to draw your Morse circle to scale, you will also need a compass, okay? I'm going to pause now and ask questions, and this is where we will end our lecture today. This is where we will end our lecture today, and we're gonna pick it up from next class, okay? Because our your last homework, we need to finish this for your last homework. Okay, any question?
So we need to learn how to draw more circle.
Yes, we at the end of the lecture, once we finish the lecture, you will know how to draw the Morse circle.
Okay.
And we'll also do worksheet on that.
All right.
Professor, I just want to ask one more time. You said we'll get the stuff graded when?
Yeah, I have already graded your midterm 2. It's just that I haven't made it available. I did not submit the grades.
Oh, no, I'm talking about the quizzes that we took like a month ago.
Yeah, the quiz, you're going to get it by Thursday.
This Thursday?
This Thursday.
Okay.
Anybody with any question regarding today's lecture? Everybody good?
Yeah.
Good.
Okay, let me see. I have one in the chat box. Okay. Okay, that's Douglas. Jose. Okay. All right. So, okay, people. So next on Thursday, we're gonna meet, and hopefully, I don't think we would be able to cover any of the more circle on Thursday. We'll mostly be covering the midterms. I'm hoping to cover both midterms next Thursday, but let's see. Okay.
So you'll post the grades by Thursday?
Yeah, midterm 2 is already graded. I just did not make it available because I'm
Okay.
attaching. Some of you, I had to actually download. It did not appear. Some of you should be able to see some of the comments already in your, if you open your submission.
Blackboard, yeah.
Oh no, you won't, because I did not submit the comments. So you won't be able to see the comments, okay?
Yeah.
But some of you, I had to actually download it and separately grade it. So for them, I have to send it as an attachment. So yeah, so I'll do that. You guys should be able to know the scores by Thursday. So it was good, very good, I would say.
Can you make final a little easier?
What? Your midterm
No, I ran out of time. I was like running out, like
No,
I was out of internet and stuff.
because you made a mistake, Amir.
I know that.
Not like
That's
that.
why you.
I always make mistakes. That's the point. That's why I'm in college.
You know what was your mistake? I was grading your copy, and I think I remembered the mistake. It's not only yours. A lot of some of you ran out of time because you were calculating moment of inertia, whereas I provided the value for it in the question.
Yeah, I didn't notice it until then. I wrote it down in the comments too. I told you, like, I need more time.
Which question, Professor? The last question, part 1?
No,
No, not the last one. Problem section B, problem 1.
Yeah, so section B, part 1. Yeah, okay.
Problem 1. Yeah, the moment of inertia was given.
Yeah.
So you didn't have to waste your time finding it.
Yeah,
Okay?
actually, I felt like the second problem was way easier than the first one in section B.
Well, it's a trade-off. Like in the second problem, I made the moment and then shear force diagram easier, but then you had to calculate Q and others. Some of you struggled to calculate Q and things that.
But you covered that in the YouTube
I
video.
did.
I did. Yeah.
But in the first problem, you didn't have to calculate your I or anything. Just have to calculate sigma, which is minus my by I.
Right.
That's why your shear force bending moment diagram was a little harder than the second one. So it was a trade-off. I would say that it wasn't anything like one was very easy, the other was hard. It was a trade-off. But anyway, people, I'm going to end the class here then. I'll see you guys on, talk to you guys on Thursday.
Right.
Thank you.
Professor.
Yeah, no problem.
Thank you.